Hi, I'm the last talk before lunch. So I'm going to be talking about high-speed polymer sol gel waveguide modulators for RF and communication application. My name is Shabnam Virji. I'm from the University of Arizona. So here are our typical modulator goals. We've got two different goals, one for RF photonics and one for optical communication. In general, we're working at 1550 nanometers and we want to operate below 7 DC. And the main difference between the two are their loss and V-pi measurements, with the loss being much lower for optical communications and V-pi being lower for the RF photonics. And there's various applications, both commercial and military. And then here I show one of our packaged modulators that we designed in our new package design. And I'll talk about that later. So why are we using EO polymers? Basically, we want to try and replace the lithium niobate modulators with the EO polymers. And in this case, the EO polymers are much better because their Poco's coefficient can be modified based on the side chains that you modify on the chromophore. And we can go down to 0.5 volts in the drive voltage. And we've also gone down to 4 dB loss with ion exchange waveguides. And then these are some of the polymers that we've used courtesy of AlexGen. And APC is our host polymer. In addition to EO polymers, we use modified sol gels as our cladding layers. And so sol gels have a number of advantages, including their low temperature, their refractive index tuning, just by mixing different amounts of starting materials. They're photopatternable. And so we use MAP TMS, diphenyl diethoxysilane, and then zirconium propoxide. And if you add different amounts of the starting materials, you can tune the refractive index so you can guide the light in a certain direction. So previously, we've designed high delta N strip-loaded waveguide modulators. And so it consists of 3 different layers, basically. So in the passive section, you've got the 1.45 refractive index and then 1.539 for the core. And then this is the EO polymer layer that's photo bleached, and it's 1.1 microns. And so when you don't photo bleach the polymer, the refractive index increases, and so you created a strip-loaded design, and so the light wants to go through lateral confinement into the EO polymer. And so we've seen 5.7 dB loss with a high NA fiber. But in this design, it's limited because we can't make polarization maintaining high NA fiber. So we've modified this design to have 2 transitions instead of 1 so that it matches with an SMF fiber. So in this case, all we've done is, in the previous design, we've added 50-50 MAP TMS, 5 micron thick, so that we get good matching with the SMF waveguide. And so we see the taper of the sol gel being the transition 1, and then the transition 2 is the photo bleaching of the EO polymer, so we can tune the refractive index. And so here is an optical picture of our waveguide. So our waveguide dimensions are 10 microns by 2.5 microns. And then these are just the various layers of the cladding and the EO material. So a major problem that we've been having is adhesion of the EO polymer to our sol gel film. Because the EO polymer is more organic and the sol gel is more like glass, we're having trouble getting it to stick well. And so if you look here, you can see it peeling when we dice it. And so I found that if you use this 3-aminopropyl triethoxysilane as an adhesion modifier, it covalently bonds to the APC and it enhances the adhesion. So when you dice it, you actually don't see any of the peeling after the fact. And that helps because then when you go ahead and attach the electrical interfaces, you can wire bond and you don't see that peeling. And so we're using these K connectors for our electrical contacts to our package. And here's a little cartoon of the modulator with the fiber blocks and the K connectors. And so basically, this is a picture of this pin right here. And these 2 are the grounds, and that's the center pin. And we can wire bond to it. And we can wire bond, and if you guys are not familiar with wire bonding, basically it's just vibration on top of a heated substrate. And so we can heat up our substrate only so much, because then the chromophore would go out of its poled state. And so we work at a low temperature, and we have a new edge bonder that works really well for this. And so here's our package picture that I showed you in the beginning. So we use low shrinkage index matching UV epoxy for the modulator, and then these are the RF outputs. And then these little tiny pins have wire bonds to them. Basically, you can't see it at this level. And so these are our diced modulator chips. They're just a little bit longer than a dime, and they have 15 millimeters electrode length, and we get a high yield dicing process. So in conclusion, we've seen EO polymers that enable high performance devices. We've got enhanced adhesion for the polymer to the sol gel, and then the sol gel tapers and the EO tapers produce new device designs, and then we've got high speed connections by wire bonding, and we get a nice high yield for the dicing process. And acknowledgements. Thank you.